before we take FETs, let us recall an example which we had taken last time and it didn't quite finish. It was a BJT with a 27K resistor here and a 2 volt source, DC source. Then this was grounded. There was a 500 ohm collector resistance and this went to a 10 volt source. The problem was to find out I sub C and VCE, the DC values. It was given that VBE is equal to 0.65 volt, beta was given as 150 and ICEO tends to 0. These were the given quantities, and we found out that I sub C is equal to 7.5 milliampere and VCE is equal to 6.25 volt. This is what we found. The next part of the question says, suppose in series with this 2 volt source, suppose there was a small AC voltage source of value 0.68 sine of omega t. Suppose there was a small AC voltage. Why do I say small? Because compared to 2, this is small, okay, 0.68. Now you notice that the maxima and minima of the voltage that is applied to the end of 27K is 2.68 and 1.32, whereas this voltage is required to be 0.65. Alright, so it is within limits. Suppose this AC source was such that the voltage here fell below 0.65, then there is a possibility that the transistor could be led to cut off. Alright, okay. Now what we want to find out is, if this is so, then obviously obviously between, well, let's look at the collector current, the base current. Obviously I sub B would be the DC value. What did we found the DC value to be? 50 microamperes. 50 microamperes plus an AC quantity, which is required to be small compared to the DC value, in order that the emitter base junction is in the active region. Okay, we will find this out. Now if this is so, if the base current has an AC component, naturally the collector current shall also have an AC component now, and the voltage between the collector and emitter shall also have an AC component. We want to find out this AC component, which obviously we shall denote by VCE. Okay, we will find out VCE divided by 0.68 sine omega t. That is the AC component of the voltage developed across the collector and emitter divided by the signal voltage that you have applied. This is the signal voltage, 0.68 sine omega t, and this shall be the gain of the amplifier. This shall be the gain of the amplifier. That is, given an AC voltage 0.68 sine omega t, we get an AC voltage across the collector and emitter, which will also be of the form K sine omega t, but this K will be greater than 0.68, and therefore there shall be a gain. In order to find out what this gain is, let's look at the equivalent circuit, AC equivalent circuit. In terms of AC, what you have is 0.68 sine omega t, then ignore the DC value, you have 27K, and from base to emitter the DC voltage is 0.65 volt, that does not change. What we have is a resistance R pi, which is equal to 26 millivolt divided by IC or IE? IE. Okay, how much is IE? IE is approximately equal to IC, right? And therefore we take 7.5 milliampere, then this must be multiplied by beta, which is 150, and this is approximately equal to 520 ohms. Actually it should be beta plus 1 to be exact. It should be 151. If you are divided by the base current, that would have been correct. No beta plus 1 factor is needed, but since we are divided by the emitter current, which is the same as the collector current, this is 520 ohms. Okay, and then we have the AC equivalent circuit shall have simply a current generator of beta times IB. Beta is 150 and IB is 50 microampere. Therefore this is what will be the current generator, beta IB. Then ICEO is not required. It is not that it is negligible, but it is not required in the AC equivalent circuit. And then we have N R sub C, that is the collector resistance, which is 500 ohms, and this is the voltage VCE. We have thrown out all the DC quantities, the batteries and their associated paraphernalia. Okay, so what is VCE then? VCE is equal to, this current generator flows like this, and therefore it will be minus the current 150 multiplied by 50 microampere multiplied by 500 ohms. Yes, we have not found out IB.
Yes, sir.
Now we have to find out IB. IB is not 50 microampere. No, this is the DC value.
Yes.
How come you didn't object to it? This is the DC value. This is not correct. I'll answer your question a little later. Let me correct this. Do not agree with whatever I say. I must put here the AC value. Now what is the AC value? I sub B, I small I subscript small b is equal to 0.68 sine omega t divided by 27k plus 520 ohms. Correct? So you convert this 27 times 10 to the 3, add to 520, and the result is 25 sine omega t, so many microamps. So this is 25 sine omega t. This is 25 sine omega t. Is the point clear? Where we made a mistake? We cannot use 50 micrometers, that's the DC value. We must find what the AC I sub B is. Alright? Now if I do that, then VCE comes as minus 1.875 sine omega t. You see, it is of the same form as the input signal voltage. It was 0.68 sine omega t, this is minus 0.1875 sine omega t. So the gain is the ratio of the two, sine omega t cancel, and we get gain as minus 1.875 divided by 0.68, which is equal to minus 2.75. This is the voltage gain. Okay, this is the voltage gain, that is the output signal component divided by the input signal component. Alright, voltage gain. What is the current gain? That's exactly equal to 150. Agreed? This is equal to beta. See, output signal current divided by input signal current. Okay. Now you notice that there is a negative sign here. So the gain, okay, let me go back here. The output voltage signal component has been found out to be minus 1.875 sine omega t. Apparently there is no phase change, because this is sin omega t, the input is also sin omega t. But you must recall, you must remember there is a negative sign here, which means a phase change of 180 degrees. In general, it may be 180 degree or 180 degree plus some other component phi. As you shall see later, when you take the transistor capacitances into consideration, then there is indeed a phase change which is different from 180. Therefore, there is a phase change here of 180 degree. Now I can take your question. Yes.
So, in the small signal
speak loud. Yeah.
In the small signal model which we have considered in this problem,
correct.
In the output part, we have not considered any early resistance.
In the output part, we have not considered. Yes. Okay. Okay. Actually, what we should have done is, from here, we should have introduced a resistance R sub R0. But let us see what R0 is in this case. Let us say that the early voltage is 100, and early voltage lies between 30 and 150. This is the range, usual range for silicon transistors. This divided by the collector current, which is 7.5 milliampere. So how much is this? This is K. It is of the order of more than 12K. Isn't it right? And 12K parallel with 500 ohm is approximately 500 ohm. That's why we have ignored. R0 is usually very large compared to RC. But in situations where the load resistance is very large, you do have to consider R0. Okay? Alright. Now, this leads us to a consideration of FET. More problems on BJT shall be worked out day after tomorrow, Thursday class, and in the tutorial class. From the tutorial sheet that I have supplied, some of the problems will be done in the tutorial class and the rest will be done. The tougher ones will be done here by me. Okay. We now go to a consideration of FET. FET, I am told that not much of FET has been done in 110. So we would like to look at FET a little more deeply to be able to understand its circuit models and its performance as an amplifier. As you know, F stands for field, E for effect, and T for transistor. This is a field effect transistor, which means that the basic conduction mechanism in FET should be field oriented or field induced. That is, you create an electric field, and you allow the carriers to be drawn away by the field, or carriers to be accelerated by the field and go to a collector. Now, in contrast to a bipolar junction transistor, where conduction occurs basically due to diffusion, due to the flood of electrons coming from the N region and crossing over to the collector region, collector N region. So field effect transistor is basic mechanism of conduction is different. Historically, field effect transistor was conceived much earlier than BJT, but because of fabrication difficulties, a commercial FET had to wait till about the middle of 60s, 1964-65, commercial FETs came in the market. Whereas the bipolar junction transistors had flooded the market right in 1949 or 1950. Okay, 1947 of course was the year. 1948 was the year that transistor was first disclosed. Within a year, Bell Telephone Labs themselves, which was responsible for the invention of the transistor, Bardeen, Brattain, and Schottky. 1949 itself, commercial BJTs came in the market. They were not very good, but gradually they were improved. Whereas FET had to wait for a long time for improvement in technology. As I said, besides the mechanism of conduction, there is also a difference that FETs are unipolar in contrast to BJTs, which are bipolar. Bipolar because there are two kinds of carriers, electrons and holes. On the other hand, in an FET, the carriers of current are either electrons or holes, not both. The basic phenomenon that occurs in an FET is, suppose you have an N-type material. A very simple way of representing an FET. Suppose you have an N-type material, okay, and you have a metallic connection here, a metallic connection here. I am taking a cross section, okay. Now, obviously, if you connect a battery between these two terminals, a current will flow. The N-type material will act simply as an ohmic resistance. The electrons which are available will simply drift towards the positive potential. Suppose you connect a positive potential like this, then electrons will be drifted towards this, okay. Conventionally we say this is the source, because electrons going away, the battery has to supply electrons. So electrons, this terminal is the source, and this terminal is the terminal at which electrons are drained away. The terminology is slightly different. We could have called it a collector, but conventionally it is called a drain, a source and a drain. If this is the situation, then it is nothing different from an ordinary carbon resistor, for example. Okay, across a resistor, it's a semiconducting material, so the conductivity is in between that of a metal and an insulator. Besides that, there is no other difference. It's an ohmic resistance. Now, what is done is, if this is the way, then this is called a channel. That is a channel through which water flows, canal through which water flows, channel through which carriers flow. So it's an N channel. The conduction of the N channel is due to electrons only, so it is an unipolar device. This current is controlled by a field applied between this terminal. Let me use some other color, between let's say some mechanism which I shall come a little later. This terminal, while these two are connected together, I am showing a cross section, so from the top as well as bottom there is a layer, which I shall say what the layer is a little later. This is called a gate. By application of a voltage between the gate, between this terminal and the source, by application of a source of a voltage between the gate and the source, the width of the channel is controlled, or the flow of electrons in the channel is controlled. And this is how the third electrode comes. If you compare with a BJT, gate is comparable to the base, the source is comparable to the emitter, and D, drain, is comparable to the collector. Now, how this is done differs from FET to FET. There are various types of FETs, and we shall discuss the family tree in a minute, but let me tell you how this is done. Suppose this material is P. Suppose there is a P-type material deposited on the N channel, okay, and suppose there is a battery connected like this, okay. Then obviously the source which is connected to an N-type material and the gate which is connected to a P-type material, obviously there is a reverse bias that is created between the gate and the source, and because this is resistive, the reverse bias will be 0 here and will increase to a maximum at the gate. Is that correct? In this channel, the reverse bias will increase like this, because it's a resistive material. This voltage is dropped from here to here, and therefore there will be a potential gradient, okay. In other words, what will happen is that the depletion region in the entire, there will be created a depletion region, because this is a PN junction reverse bias, so there is a depletion region. The depletion region width shall vary along the channel and will be controlled by this voltage VGS. Alright, this is the control. By appropriately controlling VGS, and by appropriately choosing VDS, one can get amplification in a field effect transistor. The phenomenon is exactly the same, exactly of the same qualitative nature as that occurs in a BJT. That is, a gate controls the flow of current in a channel. The current is carried by a single type of carrier. That is why it is called a unipolar device, in contrast to bipolar BJT. Let's look at the before we go to the family tree, let's also realize that instead of a PN junction, I could have a metal deposit here. Okay, instead of a p-type material, I could have a metal. Now you know there are metal rectifiers, metals and semiconductors, copper and copper oxide, for example, or selenium rectifier. You have heard of selenium rectifiers? Metals in contact with semiconductors can give rise to rectification, because there is a difference in work function or the contact potential. Basically it's a contact potential. So instead of a semiconductor material, one could have a metal semiconductor gate, and such devices are known as MESFET, metal semiconductor field effect transistor. This is called a junction field effect transistor, or JFET, junction field effect transistor. There is nothing sacred about this type of channel. You could have a P channel also, then the biasing would have been different. Agree? So a JFET could be either P channel or N channel. Similarly, a MESFET could be P channel or N channel. But MESFETs we take out of consideration. They are applied, they are not applicable, they are not favored at lower frequencies. They are very useful devices at microwaves, so we will not consider them. As I said, JFET could be either P channel or N channel, but however N channel is preferred because of the higher mobility of electrons as compared to holes. So we will mainly, just like BJTs, we are taking NPN as the basic material. It's not that PNPs are not used. For example, in a complementary symmetry, you require an NPN and also a PNP. Okay. Now, in JFETs, N channel devices are preferred because of the higher mobility of electrons. The third way that the electron flow in the channel can be controlled is to have a capacitor. That is, you have a let me draw it separately. You have an N channel, and then what you do is you deposit an oxide material here, and this oxide is silicon dioxide, because the basic material is silicon. So you simply expose to oxygen when silicon dioxide is deposited. Silicon dioxide is an insulator. Okay, silicon dioxide is an insulator, and then you deposit a layer of metal here. Okay, so this is metal, this is silicon dioxide, and then you have the semiconductor N. All right. So what you have is metal oxide semiconductor. This is the architecture of the FET, and it is therefore called MOSFET, metal oxide semiconductor field effect transistor. This is another way that the channel current can be controlled. Obviously, the channel current is being controlled through capacitive effect. If you apply a positive potential here, for example, what will happen? No current can flow through the gate because there is an insulator in between, but electrons will accumulate here. Isn't that right? Electrons will come over here because of the capacitive effect. This is positively charged, and therefore this must be negatively charged. And by controlling this voltage, the accumulation of electrons here can be controlled. Now, if electrons are bound here, obviously less number of electrons will be available for conduction. All right. On the other hand, if this is negatively charged, then holes will come here, and therefore more electrons will be available for conduction. This is the way that the electron current in the n channel can be controlled. There is a source here, there is a drain here, and the current, the electron current can be controlled. So the third type of constructional feature of an FET is through metal oxide semiconductor. Now, with this brief introduction, let's have a look at the family tree of FET. This is available in most of the textbooks, so you don't have to copy this. I have started from field effect transistors. Field effect transistors can be either junction JFET or insulated gate or metal oxide semiconductor. Sometimes we call MOS FET also as IGFET. This was the earlier term, but currently we use MOS. They are identical. Insulated gate FET. Okay, these are the two basic types. Now, junction FET can be, the basic material can be either silicon or gallium arsenide. Gallium arsenide is mostly used for microwaves. Therefore, we shall not consider this in this class. We'll consider FETs made of silicon only. Okay, and as I said, the junction could be created either by semiconductor PN junction or by metal semiconductor junction, and this also is of major applicability in microwaves, so we do not consider this. Now, junction FET basically occurs in depletion mode because a PN junction is reverse biased and there is depletion created. As you will see, MOS FET can work either in depletion or in enhancement mode. That means it can enhance, it can create more electrons, and it can enhance the current flow. Now, as I said, junction FETs occur in depletion mode, and they could be either P channel or N channel. On the other hand, MOS can again be made of silicon or gallium arsenide. Gallium arsenide, once again, is of applicability in microwaves. All right. In silicon, there are various types of FETs. These are some of the samples. For example, CMOS, for example, NMOS is N-channel MOS. PMOS is P-channel MOS. There are many other nomenclatures. CMOS stands for complementary MOS. Some of these you will get to know in details in the digital integrated circuits. For example, HMOS is high performance metal oxide semiconductor, DMOS is double diffused, and so on and so forth. Now, metal oxide semiconductor, as I said, can work either in depletion mode or enhancement mode, in contrast to junction FET. Junction FETs work only in depletion mode. Okay, and in each mode it can be either a P channel or N channel. This is the tree of FET. One can ask at this point, why FETs? If BJTs can do all the jobs, then why field effect transistors?
Speed.
No, speed is not the consideration. Actually, speed may be less because of capacitances. You see, in the metal oxide, you are introducing a capacitance between the gate and the source, gate and the drain. There is a capacitance, and capacitances usually reduce speed. The size, that is correct. And you see, the packing density of MOS device is much higher than BJTs, and the trend is for smaller and smaller integrated circuits, and therefore MOS has become very popular. Most of the chips that are available, unless speed is a consideration, are made of MOS. On the other hand, if speed is a consideration, BJTs have to be used. Sometimes one makes hybrid technology, that is BJTs as well as MOS on the same device, and these are called BiMOS circuits. BiMOS means bipolar junction transistor and MOS transistors, a combination, so they are called BiMOS. Okay, now the symbol that is used for FET is like this. The symbol that is used is, for an N channel FET, we indicate this. Note the direction of the arrow. The gate points inside, the gate points towards, and then D and S, there are two, the source and the drain, they are mostly interchangeable. Okay, the source and the drain, there is nothing to choose between them. On the other hand, in a bipolar junction transistor, you know, the emitter region is more heavily doped than the collector region. The collector region is a much larger area because it has to dissipate heat. In a junction FET or MOS FET also, it is possible to have a drain part which is different from the source part, but usually they are interchangeable. They are not interchangeable in a BJT. In a BJT, the performance degrades considerably if the collector and emitter are interchanged, whereas it doesn't happen so much in an FET. For a P channel, the arrow points out. Now, for an MOS FET, in order to distinguish between the junction and MOS, well, one extra terminal is introduced. You can see for enhancement type, there is a break here. The gate is similar, the arrow is here. The significance of these symbols would be clear when you understand, when you go through the physics of MOS devices in a later elective course. For an N channel, there is no break, it is simply an arrow like this. But let me tell you, as far as circuits are concerned, amplifiers and other linear analog circuits, it doesn't matter what the FET is, whether it's a junction or an MOS FET, the circuit model is the same. Circuit model is the same. One difference that you should observe, you should immediately conclude about between BJT and FET is that the input impedance in a bipolar junction transistor is very small, because the input is a forward biased junction. A forward biased junction offers very little resistance. That's why R pi is at the most of the order of a K. On the other hand, here the input is between gate and source, and the gate and source is a reverse bias junction or a metal oxide semiconductor configuration, and therefore the input impedance should be very high. Is that clear? So an FET is basically, if input impedance is very high, then what do you apply? You apply a voltage source. So it is voltage controlled. FET is said to be a voltage controlled device, whereas a BJT is a current controlled device. Although you shall get voltage amplification or current amplification from both, but basic mechanism is that FET is a voltage controlled device and BJT is a current controlled device. Here is a color picture of a simplified FET configuration. I have shown a junction, the coloring is mine, this Xeroxing was in black and white. This is schematic diagram, it is not the actual diagram of an FET, but to understand what happens in an FET, we briefly look into the physics of FET, briefly and qualitatively. Okay, this is the N-type box. This whole box is an N-type semiconductor. The box which I have shaded with gray, light gray. Okay, and it contains majority carriers are electrons. There is an N-type material, majority carriers are electrons. On two sides of this box, this side and this side, there are metal depositions. So this is ohmic contact, this is also an ohmic contact. The left side conventionally is called the source, the right side conventionally is the drain. Okay. Between the source and the drain, as you can see, there is a voltage VDS, positive here and negative here. So that the electrons are attracted towards the drain. Actually, the actual drain current flows in this direction, correct? From the battery positive, it goes in this direction. But electrons come and are drained away to the positive terminal of the battery. Okay. The control is created by the gate, which is through deposition of a p-type material on this side, and these two are connected together. Okay. This two, there is a metallic contact here, only gate contact, there is a gate contact here, these two are connected, and between the gate and the source there is a reverse bias. You see VGS, the negative is connected to P and the positive is connected to the N-type material. So it is reverse bias. Yes.
What is the approximate size of
What is the approximate size? Micron. A few tens of microns. It's very small. And the tendency is to go lower and lower dimensions, okay, as small as possible. Now, therefore, this junction P and N, this is reverse biased, this is also reverse biased. Now let's see what happens through a cross-sectional diagram. Is there any question on this? The geometry? It's a fairly simple geometry, and this is why it was conceived much earlier than BJT. Actually, Schottky first hit upon a field effect transistor, but he couldn't make it, and therefore it had to wait for many years. Now I have shown here a cross section of this box with VGS equal to 0 and VDS also equal to 0. No voltage is applied. Let us see what happens. This junction, PN junction, as you know, will develop a depletion. Correct? Electrons will cross to the p-type material, and holes will cross to the n-type material, and they will create a static space charge, a charge separation. So this is the depletion region. There will be a region at the metallurgical junction where there are no carriers. Okay? The carriers move over to the other side and create a vacant land, a no man's land, called the space, called the depletion region. Depletion region is cross-hatched here, and it's of width y0. Okay, and this width is the same throughout. There is no bias. Okay, because VGS is 0, VDS equal to 0. Now suppose VGS is retained at 0, but VDS is increased to a few volts. A small voltage is applied between the source and the drain with this polarity. Then what will happen is the reverse bias increases from source to drain. It is reverse biased, you understand this? Because the n-type material is positive and the p-type material is at 0, right? So the relative voltage is negative in the p-n junction, and therefore this is reverse bias. Reverse bias increases as we go along the channel, and therefore the depletion region becomes modulated like this. Depletion region becomes curved like this. Is that clear? The depletion is highest here because the reverse bias is highest here, and it is the smallest here. Agreed? It becomes modulated like this. However, current starts flowing because of the battery. Now if you increase the battery, voltage, what will happen? More current will flow. How does this current flow? They don't flow by diffusion, they flow by electric field. A field is created between D and S, therefore the electrons are moved away from the source towards the drain.
So how is the reverse bias increasing along the length?
Okay, what is the reverse bias here? The battery negative is here and it is connected to the gate, so the reverse bias here is 0. Reverse bias here is exactly equal to VDS. So and it's a resistive material, so the bias continuously increases. There is a drop across the n-type material. Okay? No, that's not clear? No. You see, let's take this end. At this end, what is the difference of voltage between the n-type and the p-type material? 0. Isn't that right? Because its VGS is connected here. And at this point it is the highest. At this point it is VDS. Therefore the bias goes from 0 to VDS along the length. So it continuously increases. And it's a resistive material, mostly this increase is linear. But the depletion region becomes curved like this. Current starts flowing. If you apply more VDS, more current will flow, because it's basically a resistive material, till a certain peculiar phenomenon occurs. And this phenomenon, before we discuss this phenomenon, I'll come to this phenomenon a little later. But suppose, consider another situation. A situation in which VDS is maintained at 1 to 2 volts, a small positive voltage, and a VGS is applied, a reverse voltage with negative connected to P and positive connected to N is applied. If it is applied, then what happens? There was a depletion region like this. In addition, VGS creates a further depletion. So the profile changes. Okay, the profile changes. Suppose VGS is increased, the reverse bias is increased. If the reverse bias is increased, this is reverse bias. Let's go back to the VGS equal to 0. When VGS equal to 0, ID versus VDS, this will be linear because it was a ohmic material. Okay. Now this linear variation obviously shall be affected if VGS is made negative. If VGS is made negative, obviously the current shall decrease. So if VGS is some quantity, let's say Vp by 8, then the current shall still rise linearly, but the value of the current will decrease. Therefore the current is being controlled by VGS. And if VGS is negative terminal connected to P, positive to source. So this junction, PN junction between the gate and the source is reverse biased. If this reverse bias is increased, a point will come at which the depletion region, the two depletion regions will meet somewhere near the gate. If that happens, then you have emptiness all around. There is no electron, alas, no electron can cross to the other side. Correct? So when VGS reaches a voltage Vp, which is called the pinch off voltage, because the two depletion regions come and meet here. They look like a pincher, and the current becomes equal to 0. The drain current doesn't flow. So VGS can completely kill the transistor conduction, which means that VGS can make the transistor, what is the language? Cut off. No current flows, so it's cut off. VGS can make it cut off, or VGS can make it conducting. Okay, it can make it conducting to varying degrees by varying VGS. Okay, is this point clear? But since VDS is small, the variation is still linear. That is, it's still ohmic. The region, the N channel, still is an ohmic resistance. It behaves like exactly a small ohmic resistance. Now we go back to the situation where VGS is equal to 0. VGS is equal to 0. In between we have taken a detour, and VDS is increased. Now initially, as I said, VDS, if VDS increases, the current increases because it's ohmic resistance. This is the characteristic for VGS equal to 0. Okay, the upper line. The initial portion is ohmic; it increases linearly. Then obviously a pinch off condition will occur at this terminal, at this point. The two depletion regions will gradually try to merge towards each other, and we expect that the current should be 0. No, but then as soon as they merge at the drain terminal, a very interesting situation occurs. The material no longer remains an ohmic material. The electrons, which are the carriers, they acquire so high a velocity that they pass through the pinch off and get collected by the drain. Not only that, the velocity of electrons attains a saturation value due to collisions. The high field electrons, when they try to go over to the drain, they are in a hurry, they collide with each other, and this collision, it's a statistical phenomenon. There is deep mathematics involved in this, but the end result, as far as circuits people are concerned, electrical engineers, the end result is that the saturation reaches the velocity reaches a saturation value. And if that happens, then the current levels off, the current becomes constant. It doesn't become zero. The current levels off at this value, and with VGS equal to 0, the value at which the current levels off is called the ID, the drain current under saturation value. It is called IDSS. This is the nomenclature that is given to it. For this typical transistor, it is 5 volt, 5 milliamperes, IDSS. Okay. Now, this is the situation when VGS equal to 0. Suppose now VGS is made negative, minus 0.5. Then obviously this saturation will occur at a lower current, right? Because VGS negative means it has controlled, it has reduced the, it has increased the depletion region, so it is controlled. So it will occur at a lower value. Similarly, if you increase it to minus 1, minus 1.5, minus 2 and so on, the current will continue to decrease till VGS reaches the pinch of voltage. And at the pinch of voltage, no current shall flow, and this line, the VDS line, is the line for VGS equal to VP, and VP here is minus 3 volt. Okay, 0, minus 0.5, minus 1, minus 1.5, minus 2, minus 3. As you notice, the lines are still parallel to the VDS axis. These characteristics are very similar to BJT characteristics, except for the fact that this is more inclined towards VDS. The slope here is less, whereas in a BJT it was almost vertical at VCE sat equal to 0.2 volt for silicon, whereas here it goes right up to 3 volts, and this voltage obviously is the pinch off voltage. This in this region VDS is less than VGS minus VP. In the other region, when saturation occurs, saturation of the current occurs, VDS is greater than VGS minus VP. Okay, and if a characteristic is given, then you can immediately find out what is the pinch of voltage, VP. Obviously this region is the ohmic region where the current increases linearly with VDS. Okay, so basically the current ID is a function of VDS, but the functional nature is controlled by the gate to source voltage. Alright, now you notice other differences, that for equal change of VGS, the current does not change equally. You see the separation between these lines, and therefore FET is a nonlinear device. Even in the active region there would be non-linearities. Linear amplification is more convenient to do with BJTs rather than FETs, because the separations are not equal, these are not at equal intervals. In fact, the current voltage relationship for an FET is equal to IDSS. We are considering a junction FET, IDSS, that is that saturation value multiplied by 1 minus VGS divided by VP, where VP is the pinch of voltage, square of this, and this is what gives the non-linearity. Okay, it's a square law characteristic rather than a linear characteristic, and this is why the separations continuously increase as we go towards lower and lower VGS. Okay, this condition happens when VDS is greater than or equal to VGS minus VP, which means that we have crossed the saturation value, we have crossed the ohmic region. It is in the saturation region that this characteristic holds good. Obviously obviously this characteristic is independent of VDS. Well, it has to be so, because if you look at the characteristics, it's independent of VDS. The current remains a constant. It only depends on VGS. It only depends on VGS. However, like the BJT characteristics, where you saw that there was a slope, there was a small slope, and you had defined a resistance R0 as the early voltage divided by the collector current. Here also ID is not absolutely constant. You can define a DID dVDS at the operating point. Okay, the slope, there is a slope which is which is denoted by 1 by, it has the dimension of conductance, right? It is denoted by 1 by RD, and small rd, you understand the meaning of D, the subscript D. Small rd is called the dynamic, yes, drain resistance, dynamic drain resistance. R0 in BJT is for the dynamic collector resistance. Okay, so RD is a dynamic drain resistance, and as you can see the model for a for an FET would be much simpler. You have a VGS, here, and there is a current I sub D here. That's it. As far as the DC conditions are concerned, there is a VGS applied between, because it's a reverse bias junction, no current flows, so it's an open circuit here, and in the output circuit there is simply a collector, there is simply a drain current I sub D. So this will be the DC, well, to indicate that this is DC, this is the DC model. The resistance here, the DC resistance is very large, and therefore we don't show it here. This is a simple model. Whereas if you take the AC model, then what will happen is you take VGS and a current I sub D, which would be, I sub D would be what? How is it connected to VGS? I sub D would be proportional to VGS, and the proportionality constant would be DID dVGS. Okay, if you take this relationship here, DID dVGS, I made a mess. No, the proportionality constant is, what should be the dimension of the proportionality constant? Conductance. Okay, so ID is written as GM VGS. G is for conductance. Why this M, subscript M? M is for mutual. That is, the current and the voltage do not occur at the same point. It is not a self admittance, it is a transfer admittance, and therefore it is called a transconductance. GM is called the transconductance, and GM is by definition DID dVGS at the Q point, and if you take the characteristic, obviously this would be equal to, GM would be equal to, if you take the characteristic, what is the characteristic? ID equal to IDSS 1 minus VGS divided by VP whole squared. If you differentiate this, then you get minus twice IDSS divided by VP 1 minus VGS divided by VP, and you see that GM is indeed linear with respect to VGS. VGS is the operating point, that is the DC gate to source voltage. We will start from this point next time.